Hello, I'm Lucas. I'm an undergraduate student of civil engineering at the Federal University of Alagoas. I'm currently in the ninth semester, and I'm an undergraduate research fellow at the Laboratory of Scientific Computing and Visualization, the LCCV, also located at UFAL. In this video, I'm going to be presenting this paper developed by me and Tiago Lôbo, researcher at LCCV, which the title is Simulating Submarine Landslides, Combining the Material Point Method with a Spatial Adaptive Scheme to Improve Numerical Accuracy. First, I would like to introduce our team of researchers at the LCCV. Our research project is responsible to develop the material point method formulation to simulate practical problems. And our team is composed of professors, CILAMCE employees, that are the researchers, a master's student research fellow, and me as an undergraduate research fellow. And also, the LCCV has been developing high-level research activities related to several areas such as geomechanics, and it's been possible especially as a result of a partnership with Petrobras. So the motivation for this study comes from the concern that submarine landslides has always been caused, as once the event is initiated, either by natural causes or human interventions, they can badly affect the society. For example, severe damage to oil and gas subsea structures, thus causing serious environmental impacts. Other aspect is that submarine landslides are really difficult to be monitored. For example, during the slide, turbulent currents are formed and responsible for depositing immense volume of debris in the seabed, thousands of kilometers away from the original site. And more, they could even be the culprit to tsunamis that are a big concern to coastal cities. Because of this difficulty, we tend to use numerical methods to simulate such events. And we have also to take into account that submarine landslides involve great extensions and large deformations, imposing other obstacle when simulating such events. Thus, in this study, we use the material point method. But even with the best choice of the numerical method, not always the numerical simulations give us the expected response. For example, the appearance of numerical fractures when we use the material point method. The material point method is a Lagrangian method first created to solve problems involving large deformations and history-dependent constitutive equations, which is essential when simulating submarine landslides. In the solution procedure, the NPM discretizes the entire domain of the problem into finite elements, in which the equations of motion will be solved. In addition, the material domain is discretized into a set of particles, called material points, that will move through the finite element mesh. Each particle carries all necessary information with them, such as mass, momentum, energy, stress, and strain. But what I want to emphasize here is that we always follow 4 steps to solve a problem using the NPM. So for a single time step, firstly, we map the quantities of interest from the particles to the nodes. Secondly, we calculate the node acceleration and node momentum. Then we map those node accelerations and other quantities of interest, if necessary, from the nodes back to the particles. And lastly, we update the position and velocity of the material points, and so we can reset the mesh to a new one. So observe that after the forces are calculated, a step that is also made in the finite element method, for example, they are mapped to the material points and the material points are updated. This strategy avoids updating the mesh position, circumventing possible distortion problems. The numerical analysis software that we used and that runs the NPM was developed by the LCCV and is called DSUB, and we coupled our spatial adaptive scheme into it. Before talking about our adaptive scheme, I would like to highlight how numerical fractures are formed in NPM. For example, let's consider a scheme of a submarine landslide simulation. As particles in NPM move through the background mesh, according to the governing equations, their spatial configuration changes throughout the simulation. In some cases, particles belonging to the same body can be separated by distances greater than the mesh element size, and the number of particles in an element is greatly reduced. Such situations introduce numerical errors and might create fractures even though no fractal law is applied. To solve this problem, we created a spatial adaptive scheme. Our adaptive scheme performs the subdivision of particles based on the deformation of each particle. For example, considering the scheme of a submarine landslide simulation again. At the beginning, we have a uniform distribution of particles. As the body slides, particles will accumulate deformation and a non-uniform particle distribution is reached, which could develop numerical fractures during the simulation. Our scheme introduces a rule that verifies if it's necessary or not to split that particle. Then, particles with large deformations are divided into 4 new ones. So the rule to the subdivision takes into account the deformation at which the particles were created and the current deformation of them. The limit parameter beta tells us how much a particle can deform without being split, and it needs to be adjusted depending on the problem. New particles inherit the state variables of the old ones, such as stress and strain. The mass, volume, weight, and initial length are divided equally between them. But after the division, we also need to adjust the current position of the new particles, as they inherit the deformation of the old particle. For example, let's consider a limiting parameter beta of 1.20 and a particle with the shown initial position and deformation. In the first step, let's imagine that this particle has moved and deformed and now have a deformation of value 1.10. If we apply the rule to subdivision here, we can check that it is not satisfied yet. In the second step, this particle moved and also deformed more, reaching a deformation of value 1.25. Verifying the rule to subdivision, we can see that it is satisfied. Then we split this particle into 4 new ones with the same stress and strain fields with a correction on the position of each one. Lastly, let's consider that in the third step, this particle moved and a little bit and deformed even more. If we check the condition again, we can see that it's not satisfied one more time. So observe that after a particle is split, it needs a bigger deformation to trigger the subdivision one more time. For the results, the first case we simulated was to show that our technique do not affect and change the mechanical energy of a system. So we first simulated the actual vibration of a continuum bar that is fixed at the left side and free at the right side. The exact solution is given by these equations and comes from a simplification considering the case mode of an infinite Fourier series. The bar is considered to be linear elastic with the simulation parameters taken as shown in the table. Lastly, for our adaptive scheme, we use the beta value of 1.025. As you can see, at the beginning of the simulation, all particles of the left side of the bar are divided because of the increase of deformation as this side is fixed. And after that, the subdivisions stop. And in the figure, you can see that the exact solution for the velocity, the blue line, matches with our results, the green dots. And the mechanical energy of the system, the dashed green line, is also conserved. So even after particle subdivisions, the numerical solution agrees with the analytical solution. We show also a comparison of the stress field during the simulation in the x-axis direction when we are using our adaptive scheme and without it. And as you can see, the results are visually equal. Then, after demonstrating that our spatial adaptive scheme is conservative, we wanted to put it in a more complex scenario and also of more importance. So, in the second case, we chose a submarine landslide simulation solved previously by Dong. You can check the reference in the paper. In the simulation, the slide mass initial geometry is assumed to be trapezoidal with 48.66 meters of length and 5 meters of height. To better represent the contact between the seabed and the soil mass, we rotated the gravity 5 degrees and kept the seabed aligned with the x-axis. In the interface between the soil mass and the seabed, we assumed a maximum shear stress of 1 kilopascal and a Coulomb friction coefficient of 1. The soil mass material is assumed to be elastic with a perfectly plastic von Mises yield criterion, and we are aiming to simulate with the Herschel-Buckley model for future work. The other material and simulation parameters were taken as shown in the table, and lastly, we used a limiting parameter beta of 1.4. As you can see, when using our adaptive scheme, the particles should be divided 2 times. When not using the adaptive scheme, a lot of numerical fractures were developed, which leads to non-reliable results for the computation of state variables. Here, we also show the displacement history comparison of done results in our simulations. The blue line represents the done results, green circles are our results using our spatial adaptive algorithm, and the red triangles without it. This figure represents the displacement history of the particle to the most right of the sliding mass. And in this case, we observed that at the end, all 3 simulations presented similar displacements. And that is because this submarine landslide case presented by Dong have a characteristic of elongation, and what is most significant to it is the maximum shear stress that was specified along the contact interface between the seabed and the sliding mass. So even though in this case the displacement history and velocity responses were acceptable even with the numerical fractures, if we used the simulation to verify the contact forces with the submerged structures, for example, this simulation wouldn't produce reliable results. And then summarizing, we observed that our technique essentially avoids subsampling of particles, reduces numerical errors, and circumvents numerical fractures. Here we have the complete slide when we do not use the adaptive scheme, and we highlighted 3 regions that presented various numerical fractures to compare with when we used our algorithm. So you can see that regions A, B, and C are completely different from the ones without the spatial adaptivity. And as conclusion, we observed that our adaptive scheme showed to be conservative. State variables were correctly computed after the adaptive scheme was performed. Smaller beta values led to more subdivisions of particles, and the numerical fractures were eliminated, increasing solution quality to submarine landslide simulations. For future works, we are aiming to simulate with more complex constitutive models, to simulate in other scenarios, and to allow subdivisions only on selected regions. Thank you very much. I would like to thank the LCCV, Petrobras, and UFAO, and thank you for your attention. Feel free to contact me or make any questions if you want, and I hope you enjoyed the presentation.